camera so we can avoid any lag for the presentation of Dr. Overend. So the BTL is pretty proud today to have Dr. Overend with us for a seminar. I had the opportunity to meet Dr. Overend maybe 9 or 10 years ago at the Menser Comedy, and I was pretty impressed by this individual. I was also in contact with him during the time of BiofuelNet. And again, this guy is just amazing. We met a couple of times in Europe as well. So it is a great honor to have you with us today and for our students to hear about what you have done in the last couple of years. Pretty interesting for them and for me as well. So just a little introduction for Dr. Overend. He was trained as a physical chemist, but he spent most of his career working in technology scale-up alongside chemical engineer, as well as a research manager in renewable energy in general and biomass and bioenergy specifically. He has also been very active in addressing the issue of economic development of biomass and the challenge of access to modern energy cooking service in several developing countries, including China and the Philippines. Early career alike include working as a child chemist, looking after several nuclear research reactors, a EV water plant, and a coal-fired power plant. After a PhD in atmospheric chemistry, he continued at NRCC until the first energy crisis intervened. He then became a member of a task force to develop the first renewable energy policy for Canada. After that, he participated in its implementation as a research manager and participant in several projects, the most important of which he was joining the UDS program with Professor Esteban Chornet in developing biomass liquefaction and fractionation technology. So Professor Overend was Professor Associé in the Faculty of Sciences Appliquées at the Université de Sherbrooke for 5 years in the 80s, while he was continuing his work at NRCC. In the 90s, he joined the NREL lab in Colorado and worked in biomass to electricity project, biofuel, resource assessment, and village energy. In 2000, he was elected as a research fellow helping to steer the NREL long-range R&D program. And since retirement in 2006, he has worked in the private sector on biomass fuel development while trying to understand the barrier to technology deployment. Finally, recently retired as editor of the journal Biomass and Bioenergy after 3 decades of helping authors and researchers to publish their peer-reviewed research. So the title of the seminar will be Biomass and Bioenergy Assessment in a Broad Sweep from Deep Time to the Climate Constrained Future. So Dr. Overend, again, it's an honor to have you with us today. And at this point, I think the floor is yours.
Thank you very much. I'm honored to be invited. It's a long time since I was working at Sherbrooke and had such a wonderful time of exploring the beginnings of biomass energy conversion in the modern sense. I was also rather surprised by the invitation because it's over 3 years since I've had an active laboratory program, and I'm now truly a solo desktop researcher. And what I'm going to talk about is a perspective on where we are now and where we are going in bioenergy. And all of the viewpoints are mine, not those of any official body I've ever worked with. And I hope you find it interesting. My plan is to start 1 million years ago, which seems strange, but you will see the sense of it, when all energy was in fact provided by biomass. And now today it's less than 10%. And I'm going to go through the current usage of biomass and move on to future prospects. So starting in deep time, like all talks, we have 3-letter acronyms like the 3 Fs and the 4 Fs, a 4-letter acronym to save repeating fuel, fiber, and food and fodder all the time. 1 million years ago, a species called the hominins started to emerge in Africa. And we are the remaining member of those hominins, Homo sapiens. And it's evident from archaeology that man, as he developed, used fire extensively. both to manage wildlife, for cooking, and about 10,000 years ago, when they started with agriculture, the heat provided by biomass was used to manufacture material objects. Lime, you burn calcium carbonate to make calcium oxide for agriculture. Glass, fusing calcium oxide and silicon dioxide. Pottery, and the Bronze Age. And you'll see that the rate of growth of the hominins was fairly slow. There might have been maybe 1 million people in the almost 900,000 years to 15,000 years ago. And then the population started to grow between 15,000 years ago and 7,000 years ago. It probably multiplied by about a factor of 4. After the start of the Iron Age, biomass was really getting. If you think about how much fuel people use in cooking, 1 kilogram of iron produced by smelting consumes 150 kilograms of biomass fuel. And that probably is about what one person would use in a year cooking food. So the demands on biomass grew immensely, as did the population. And about 1,500 years into the current era, there were about 500 million people, and coal started to make an emergence, along with extensive use of wind and water power. And I'm also noting that there was a large use of biomass for fodder, as well as fuel, fiber, and food. And then in 1850, the energy and population really took off, reaching over 1 billion people. This is a complicated diagram, though should be quite familiar to those of you who are scientists. I'm going to show it blown up in the next picture, but I want to just note a couple of very important features about what I'm talking about. The left-hand axis is described as inexhaustible energy. That's to say, sustainable energies like solar, wind, biomass, geothermal, marine. And I also add in nuclear, both fission and eventually fusion, into that category. The grouping on the right-hand axis is coal and natural gas. These are the two main global warming potential substances. Coal, because it is in fact almost pure carbon, and methane, natural gas, because it has 20 times the global warming potential of carbon dioxide. So if you think about it, the whole of the natural gas system has to have a leakage rate of less than 5% if it's going to match the CO2 production. Otherwise, it's a very dangerous source. And in fact, methane is rising rapidly in the atmosphere. And on the bottom, I've put the mobility fuels, today's mobility fuels, oil and natural gas liquids. And the diagram has a series of time points on it. In the bottom left corner, at 80% inexhaustible energy, which was almost all biomass, and something around 20% coal coming in. This was the peak in recent history for renewable energy. If you move along vertically to 1900, the proportion of biomass and wind has gone down below 40%. It's in the 32% region. And the coal has risen to just over 65%. The final points on the diagram are called steps, DRS and STS, and net zero by 2025. I'll explain them in a little bit more detail in the next slide. So here's a blow-up of the previous triangular diagram. And what I'd like to trace is the trajectory. You come from 1850, increasing coal usage. You actually reach maximum coal around 1910, and then oil starts to come in and you are down to about 18% renewables in 1920. Oil continued its growth after the First World War to 1930. And then there was a Great Depression. And you can see between 1930 and 1940, it's a very short distance on the diagram. And then after the Second World War, there was a huge expansion of oil. And you can see by 1950, the oil proportion is in the middle 40s. Sorry, in the low 30s. And then by 1960, oil is nearly 40%. And then comes 1971. 1971 was the last year before an energy crisis caused by OPEC withdrawing oil from the market. And you can see how the dots then go into a huddle because people were struggling to find ways of substituting for oil and back off the oil contribution. This process continued through the 90s, and this is the period in which we developed the energy policy for Canada, in which we tried to displace oil and replace it with natural gas and with renewables and nuclear. Then there was another crisis in 1995. You see another huddle of dots. And then we resumed in the 2000s, starting to become very conscious as a society about the rate of change in climate-associated issues. And by 2019, we were starting on the pathway towards increasing renewables and less reliance on fossil fuels. The International Energy Agency, the IEA, publishes a World Energy Outlook every year, has done for about 25 years. And the latest one, WEO20, is looking at the impact of the COVID epidemic on the energy system. It's looking on the possibility of instituting major changes, and it's looking also at the necessary steps needed to reach net zero carbon emissions by 2050. And you can see that the pathway proposed is to move very steeply towards the bottom left-hand corner, which is a very high renewables and sustainable energy component and a much reduced reliance on fossil fuels. But I would also note, go back to 1930 to 1940, the distance between those two steps in change in energy mix is very small. Look at the distance between 2019 and the sustainable development scenario. It's much more like the decade of 1940 to 1950, and the sustainable development scenario is posited for 2030. So we have a task in front of us in making changes to sustainable energy and reducing our carbon footprint. Coming back to biomass and bioenergy, you have to take the early data on this chart with a pinch of salt because there wasn't a lot of statistical data gathering, but the best estimates are that in 1900, there was about just over 1.5 billion people. The total primary energy supply was around 32 exajoules. Biomass and bioenergy in something like its modern form was about 8. And something called traditional biomass, which is the same way biomass was used a million years ago, was about 9. Moved to 1950, big growth in population and energy use. Biomass and bioenergy has grown significantly. So has traditional biomass because it's proportional to the population of the developing countries. By 2010, we have nearly 7 billion people, 540 exajoules of primary energy supply, about 10% of which is modern biomass and bioenergy, and there's still a very large traditional biomass component. And in 2019, the preliminary figures are that we have nearly 8 billion people, 600 exajoules, still somewhere around 10% modern biomass and bioenergy, and a reducing fraction of traditional biomass. As Jean-Marie noted, I've spent quite a bit of my life working on development issues, and the key issue is access to clean cooking. 80% of the world's population doesn't live like us in Canada or Europe. It's low and middle income countries with a lot of poverty, a lot of food insecurity. 4 billion people lack access to clean, safe cooking. You can see on the right a typical three-stone stove from a study in Mali. And there's a couple of features of this picture that are relevant from a technology viewpoint. First of all, the technology is extremely low cost. Secondly, look at how the fire is managed. There are long branches of wood, and the woman, and it's always a woman who is working the stove, moves that long branch in and out to vary the heat, just like you turn the dial on your stovetop. And look also at the little pile of charcoal. When the fire goes out, people rescue the charcoal and they add it back in when they start the next fire. That's energy conservation. Wood is the major fuel for about a third of the 4 billion people, either in the form of such as wood or as charcoal derived from wood. There are consequences of this. Health. Indoor air pollution is 3% roughly of the global burden of disease, but is much higher in low and middle income countries. There's a gender issue because it generates inequality. Cooking and collecting food in most countries is women's work and may take several hours a day. The climate, that three-stone stove is a phenomenal polluter, knocking out about 800 kilograms of global warming potential per gigajoule, made up of black carbon, methane, carbon monoxide, and nitrous oxide. And the current estimate of the use is about 30 plus or minus 5 exajoules, and some of it is not sustainable biomass. It is deforestation, maybe about 1/3. Biomass is also used in development for institutional and industrial heating. Nearly all the technologies are artisanal, they're inefficient and polluting, and it's proving very difficult to solve this problem. A lot of my colleagues in China, in the Philippines and elsewhere, and in the developed countries have been working on improved cook stoves to reduce fuel consumption and emissions. And one of the major features of the last decade is that there is now an ISO standard which has been developed to measure progress against the key attributes of improving the cooking situation. And if you look at the attributes, it's a radial diagram. The inner ring red is bad, the outer ring green is good, and it assesses components of developing cooking systems from personal exposure to the air pollutants, which depends not only on the stove, but where you're doing it outside or indoors, the efficiency, which is fairly obvious, convenience, safety, and there's a lot of injuries from those three-stone stoves, affordability, and availability of the fuel when you need it. So how do stoves score? On the right-hand side of the diagram, you can see the score for the three-stone stove. It only just and so gets into category 3 for convenience, but every other indicator is somewhere in the range of 0 to 2. In other words, this is the very worst you can be. You can look at the emissions levels and the carbon monoxide production for tier 0 and tier 1 in the table. Now, the converse is, if you're lucky enough to have reliable electricity and you've got a well-performing electric cook stove, all of those radial arms are satisfied. However, the reality is that in a developing country, people actually have a ladder or stacking of kitchen equipment. So, home in an urban area, they will have not a three-stone stove, but a small charcoal stove in case the electricity goes off. They may try and work when there is electricity with clean and healthy cooking, but normally they're using a mixture of things. And this stacking phenomena is one of the things that's made it very perplexing in how to reduce the exposure to the pollution and the health impacts. Modern technology, of course, meets the sort of needs that we enjoy in industrial developed societies. And I hope many of you are familiar with the idea of technology readiness. Developed in the first space program, the Mercury and the Apollo program, it was a way of assessing how ready a technology subsystem in a manned capsule, for example, was to go into space. And starting at zero, which is a hypothetical, almost suggestion of a technology, through the laboratory and pilot plants, eventually you reach level 7, which is the technology is ready to be demonstrated at a significant scale. After level 7, the pioneer plants are built, and then eventually the thing just becomes normally commercial. And if you look at the technologies which have made a significant impact as energy vectors, what stands out is landfill gas and anaerobic digestion, well over an exajoule. Its uses in combined heat and power, that's CHP, direct electricity production, heat production, delta H. It's also put into the transmission grid, either as electricity or as refined methane. Pellet fuels are another one that has grown from almost nothing in the last 30 years to fully commercial and is just about 1 exajoule. It's used in co-firing, district heating, and small-scale heat. Gasification has reached a TRL of 8 to 9. There are many units in Europe with combined heat and power. There are some producing methanol, but it's not a major contributor on a scale of exajoules yet. Ethanol from starch in the United States, from corn, from sugars in Brazil and elsewhere, is also a TRL 9 and is about 2.5 exajoules on a global scale. Ethanol from cellulose, though, is almost through the demonstration phase and into pioneer plants, but is still a very small contributor to the total energy. Biodiesel, which is the transesterification of fats, oil, and greases, is at level 9 and is about 1.7 exajoules. But the big development on that side is renewable diesel. And this is hydrogenated vegetable oils, in other words, fats, oils, and greases, to make naphtha, jet fuel, diesel, and gasoline. And that's a very growing proportion. The issue with biodiesel and renewable diesel is that it depends entirely on the supply of fats, oil, and greases, which is quite finite. So if the renewable diesel is going to grow, then biodiesel will diminish. And then fast pyrolysis has been one of my challenges in my professional career, providing combined heat and power and electricity, but it's still only at the pioneer plant stage, especially in Europe. The elephant in the room is the carbon situation with respect to global warming. In the center of this diagram is the famous Keeling curve, which starts about the time I joined the nuclear industry in 1960 and rises exponentially up to October 2020. This is a data set from the NOAA administration in the United States. And the red dots show the seasonal variation as you go from one season to the other in the Northern Hemisphere. You either absorb carbon dioxide or you emit carbon dioxide. But overall, the famous trend is shown. And what's behind the trend, where we are today, is that the atmosphere has about 410, greater than 410, parts per million. In 1850, the start year on the triangular diagram, it was about 286. And if you think of the atmosphere as a bathtub filling up, because we're putting in carbon, global warming potential, the land and the ocean are taking it out, but the net difference is accumulating in the atmosphere and causing global warming, you can see that on the left-hand side, a major contributor was land use change. This was deforestation, the development of agriculture lands relative to forests, and also the clearing of lands for other purposes. Oil has contributed about 73 parts per million so far. Sorry, oil has contributed about 73. Natural gas so far is about 32. The cement industry, converting calcium carbonate into calcium oxide for incorporation in the built environment, makes a significant amount, 5 parts per million. And then coal, of course, is nearly 100 parts per million. After many, many years of work under the IPCC, you can see that we've managed to get the balance to the point where there's only a deficit of about 15 parts per million between what we know is going into the land sink, what is going into the ocean, and what is accumulating in the atmosphere. In other words, the science behind what is happening is well understood and really has been for nearly 30 years, but this is a very concrete expression of it. So research and development in biomass and bioenergy is being driven by the energy climate issue. And it's very interesting. We're doing a natural experiment, if you like, looking at how different countries or regions approach. In North America, and that's Canada and the US and also Mexico, the emphasis has been on research and development, which is, if you think about it, slightly perverse. Not only for its incentives, but we are concentrating, therefore, our efforts at TRL 2 to 5. We've made huge investments in that. And the incentives to adopt the technologies that are being developed are rather poor. That's not to say that there aren't some bright spots, because states and provinces do have a very big say in policy. And California and, for example, Quebec look very European. But and Idaho may look a little bit more because it's a major producer of ethanol, but most of the US states otherwise are very much sticking to oil and gas and reluctantly giving up coal. The European Union has strong R&D, but about 20 years ago realized that there had to be a scale-up and adoption strategy. And they did this through goals for appliance and vehicle efficiency and targets for the share of renewable energy. There's an anomaly which I want to highlight because it's continuing. Ethanol in the United States is billed as an energy vector, but in actual fact, it's primarily an agricultural support policy because corn is king. And one of the interesting little features is the flex fuel vehicle, which was developed between the agriculture and the auto industries to get around the corporate average fuel efficiency. Because if something was using 85% ethanol and gasoline, it was considered to be a very climate efficient, if not fuel efficient vehicle. And there's a list of vehicles that can be in this category. And look at the engine sizes, 6 liters, 5.3 liters, 5 liters. There are E85 pumps for flexible fuel vehicles. Federally in the United States, they are at fuel depots. On the normal highway, they're very evident in Iowa, but almost anywhere else, there are none. In other words, people are driving around in flexible fuel vehicles and using only gasoline. The other anomaly is that small refiners were impacted by the rapid growth of ethanol, which is fairly obvious. That was the whole point. You were trying to replace gasoline, a fossil fuel, by a renewable fuel. So they got the EPA to agree to waive their obligation to buy renewable energy credits. They're, in the United States, they're called RINs, and their life cycle renewable identification numbers. The renewable energy supplier generates the RINs, which are then separated from the physical fuel. These are traded, and people who have to offset their fossil fuel purchases, emissions, and retire them. And so they were allowed to not meet their obligation for fuel blending. So the net effect is that it's a policy that's had very little outcome. The EU took a different tack and made the goal the amount of emissions of carbon dioxide per kilometre. Again, there was a couple of perverse consequences. It encouraged the use of diesel in Europe for light-duty vehicles. And by now, everyone is aware that diesel engines in general are high emitters of nitrous oxide and particulate. But it also has encouraged electrification of the light-duty vehicle fleet, and they have very, very strong goals for 2030. So what is the future for biomass and bioenergy? I remind you again that those hominins a million years ago were a part of an environment, the biosphere. And this is under very severe threat because we have become a very large population, very invasive of all the areas of the earth, and we're omnivorous. We eat everything. And with an average body mass of about 50 kilograms, we count as megafauna, not quite elephant size, but big. It's a very interesting concept that comes from an ethnobiologist at CNRS, Meredith Ruth Bernstein. And it puts the human being in a different framework, perhaps, but you realize that we are causing land use change, we're losing ecosystem services, we're having a lot of species extinctions, and we have further more impacts from climate change. And the biosphere is our only base for food and fodder, agriculture, forestry for fiber and fuel, and ecosystems, wildlife, recreation. And I would mention that a lot of biomass technology relies on residues and wastes. This is good, but if you talk to an environmentalist, they say, you want me to make waste so that you can make energy? Not so good. Residues and wastes are scheduled to be minimized, if not eliminated, in a circular economy. So it's something that we need to think about how we manage the biosphere and its flow of renewable carbon. So what's on the horizon? We have the implementation of the technologies that were identified as TRL 7 to 8, making them commercial in biofuels, local energy, combined heat and power, heat, electricity, putting it into the transmission of natural gas and the electrical grid for large-scale deployment, and starting the use of bioenergy, carbon capture, and sequestration. We really, really need to address that development challenge for cooking and modern energy in the lower and middle income countries. The amount of biomass going there is somewhat the same as going into modern bioenergy. And if you think about it, it could be displaced into modern uses, and you could make an awful lot of gains on health and the environment. And I would posit that one of the very big and important issues that we need to address in the R&D spectrum is that everything is pointing to an electric future. The amount of electricity is growing exponentially in the economy, but because it's a secondary energy form mostly, it really doesn't interfere in the primary energy statistics. But as we increase the contribution of wind and solar energy, what we're reaching is an awful lot of electrons. And traditionally, way back when Esteban, Shawnee, and I were working in Sherbrooke, we were looking at ways in which we would use hydrogen to extend the value of renewable carbon. For example, if you are producing methanol, the easiest way of getting from gasification to a liquid fuel or an intermediate chemical, it would take about 1.6, 1.7 tons of biomass to produce 1 ton of methanol. If you could add in about 100 kilograms of hydrogen to the syngas produced, you would use about 0.8 to 0.9 tons of biomass, dry biomass, to produce 1 ton of methanol. In other words, the use of electricity through hydrogen would really extend the biomass resource into useful chemicals and fuels. So this is one avenue that electricity could be amalgamated with biomass. But if you look at the literature, there's an awful lot of work going on in electrochemistry, battery technology, electric storage, in other words, and we're getting the insights. So what if we could use electrons per se to affect the change in biomass to make useful outcomes? Not really an explored area, but one which would be, I think, something that should be well and truly on the target list of areas of development for biomass. The next decade puts us on the threshold of going for the target of net zero. To get to net zero, we're going to have to use a lot more renewable carbon in chemicals and materials, which in many ways is a form of sequestration. If the application is long-lived, a useful polymer embodied in furniture or a building, then that is sequestration. It also means, when you look at the actual situation, that we have to start having negative emissions of carbon dioxide. And one of the means by which we can do this is with BECCS, either exporting electrons or hydrogen and burying the carbon. We looked at this at NREL in the 1990s, before the name biomass energy with carbon capture and sequestration was ever thought of. And we looked at, I had a life cycle group, and we just said, well, you know, how would it work? And in the little diagram at the top, you can see how a dedicated biomass production system with its associated inputs and transportation put into a biomass integrated gasification combined cycle plant, which is very efficient, and pumping the CO2 in underground would bury about 800 grams of CO2 per kilowatt hour. For logistical reasons, we chose to have a natural gas combined cycle to power the compressors and provide the ammonia for the system. So the total system is about 600 megawatts, but the roughly 12–15% is from natural gas. But effectively, you're putting a negative 700 grams of CO2 equivalent per kilowatt hour in underground. There's an issue with this. When you look at BECCS in 2020, nearly 30 years after we started thinking about it, we find that the technology of getting the carbon and putting it underground and burying it, either in the ocean or in geological strata, is at least TRL 8 to 9. And the carbon capture sequestration component has been demonstrated several times in Canada and elsewhere. It's expensive. The other issue is that you've got to move, very nominally, we put about 7 to 9 gigatons of carbon, or 30 or 40 gigatons of carbon dioxide into the atmosphere every year. And to start making an impact after you've done all the reductions in use of fossil fuels, you have to remove at least 1 gigaton of carbon every year. And you have to look at the issues involved, because this is a very large amount of carbon. We have to look at the technical performance, the resource efficiency, and the economic and social impacts. And biomass is not the only negative emissions technology. There are people developing CO2 absorbers directly from the atmosphere, for example. Other people are talking about using a mineral to absorb CO2 that they can mine, minimal processing, and it will absorb CO2, a serpentine mineral. So if you look at the trilemma, you've got to look at the carbon removal, energy production and use, the efficiency. You've got to look at the resource efficiency. And biomass scores badly on water use, land use. And then you have to look at the economic and environmental impacts, land use change, from the biomass viewpoint, soil erosion, the flow of essential nutrients through the biosphere, and biodiversity. We don't know the answer to these questions, but in 2030, we're going to have to start implementing them. It is a very important research area. So here I'll wrap up. Biomass and bioenergy has been one of the most successful features of the renewables revolution since the energy crisis of 1970. We are now on the threshold of an energy revolution with no historical precedent. We have to move further and faster than we've ever done. And this is against a background of the historical rate of change in energy systems. It's almost 250 years in which it went from wood to coal, coal to oil, oil to natural gas. It takes time, and we have to do this in less than 30 years by 2050. Biomass and bioenergy is good, but it's being displaced in electricity generation by photovoltaics, the glass plantation. Electric vehicles are pinching the use of biofuels. And the growing population, remember, we're still talking of getting to between 9 and 9.5 billion people by mid-century, is increasing the competition between the fuel, food, feed, and fiber sectors, which are fed from that limited land base. So I can't predict a pathway, but one thing I do know is that we have been able to innovate very well to get to where we are. So I think we can continue to do that. And with that, I thank you very much for your patience.
Thank you very much, Dr. Overend. Very interesting as usual. I will open the floor to questions from the audience. So is there anybody there that has a question for Dr. Overend? And people from my team, don't be shy, ask questions.
Or if you're shy, send me an email and I'll do my best with it.
Well, I do have one question. So recently in Quebec, the government put forward a policy so that we all go electric, or they want to ban the sale of fuel vehicle by 2035. So do you think this is the way to go? Do you think we should like ban every fuel vehicle and focus everything on the electric vehicle, at least in Quebec?
Quebec, with its population, isn't going to make much of a difference to the world.
Of course.
I'm not being mean, but it's important that we start to do things like that, whether it's in California or Quebec or in Europe. In Quebec, you have an inherent advantage. You're 90% renewables. That triangular diagram can be drawn for each province, and you can show Alberta and Quebec at the opposite poles. That's easy. So Quebec has a very interesting route with a lot of hydroelectricity, growing wind power, and photovoltaic. An electric solution is perfectly feasible. And think about it. If you tell everybody that in, I don't know, 2025, 2030, there will no longer be any sales of internal combustion engine light-duty vehicles, then everybody can make an appropriate plan. And the fleets last about 15 years. So by about 2050, there may be no internal combustion engines at all. But it's a transition that has to be managed. So setting a goal and then filling in behind it with how you will do it realistically is very important. But I think if you don't have goals, as the old saying goes, if you don't know where you're going, it doesn't matter which road you take. So think about it. We have to have goals. That's what the World Energy the World Energy Outlook did with its net zero 2050. it has outlined a clear set of goals and pathways by which they can be reached. It's well worth reading that document. Unfortunately, it's a pay-for document, so I can't share it. But practically, if you don't have a goal, you aren't going to get there.
Okay. We have a question from the audience in order of apparition on my desk. Bruna, my colleague Bruna Rego de Vasconcelos has a question. So Bruna, please open mic and camera for Dr. Overend to see you.
Sure. Thank you very much for the presentation. It was very nice. Can you hear me well?
I can hear you very well.
Okay.
Yes.
So my question was a bit related to what Jean-Michel was asking about electricity, and as well related to what we were presenting before of use of electricity through hydrogen. And here in Quebec, we're having big discussions and developing technologies that are called power to X. I don't know if you're familiar with it, for production of electrofuels. So I was wondering, what are your thoughts about that, comparing with biomass, fuels produced from biomass, and also the use of electrofuels that would be a way of using electricity, but still producing the same fuels that we're using today?
I think this is probably the best transitional strategy of all, that if you can continue to use a carbon backbone to carry renewable energy sources, then you don't have to make much change to infrastructure. I'm quite famous in the Shell Oil Company for my viewpoint on the hydrogen economy. In the 1980s and 90s, I used to teach at a Shell summer school, and they gave me the hydrogen economy. You know, they pass you a sheet of paper and they say, talk about the hydrogen economy. And the hydrogen economy is a great thing if only we'd done it in 1910. But we've built up this huge infrastructure of distribution of natural gas and petroleum, automobile industry. You can't replace it that quickly because we're 2/3 of the way there to maximum population. So it would be a major undertaking. There's nothing wrong with hydrogen. It's a wonderfully clean fuel. And with abundant electricity and better ways of getting there than making electrons and doing electrolysis, because we can make hydrogen directly from the band gap in silicon in solar cells, for example. And they just don't last very long yet. But practically, hydrogen is coming, but probably not focused on the light-duty vehicle. That's where I see it. But it used to be fun teaching the course because you had a great deal of fun. I was teaching secondary school teachers and university lecturers. They were the pupils at the Shell Summer School. And they had not thought of all of the implications of when you go to fill up your vehicle. And the one that I really blew everybody's mind is, you can do this calculation yourself offline. When you get hold of the gas pump at the filling station and you put it in and you start flowing fuel, the power, in other words, the joules per second going through that, is 20 to 30 megawatts. Think of an electrical cable which carries 30 megawatts. Does that help?
Yes, thank you very much.
Going forward to the next question, we have online Professor David Chiaramonti from Italy. So David, if you want to open your mic and camera, and feel free to ask your question.
Thank you, Jean-Michel. Thank you for inviting me to attend this interesting presentation from Ralph. And Ralph, it was always a pleasure hearing your thoughts. Just a minor comment. From the European point of view, the situation is quite confusing this moment. Cost of PV electricity has gone down to 2 € per kilowatt hour this July in Portugal. And this is the massive movement around electrification and also hydrogen, but I mostly think electrification and PTX, as you say. But my question is regarding BECCS. Of course, I may be biased because in the area where I live, the issue of carbon is getting more and more relevant. Carbon in the soil, I mean. We lack carbon and organic matter in the soil dramatically, increasing a very well documented trend. So my question to you is that maybe we should, at least in some regions, stop talking about BECCS, bioenergy carbon capture and sequestration, and rather speak about, how can I call it, BECCS is a horrible word, bioenergy carbon capture and utilization, but utilization in the sense that we are stopping the shift of carbon from the earth to the atmosphere and bringing this carbon back where we really dramatically need. And this is very much in the bioeconomy view, to have energy vectors, but also have products and carbon for us. Last week there was and I conclude with that, there was a quite intense discussion in the team of the industry of biofuels, whether to still use the term decarbonization or to shift to other kind of terms, distinguish between good and bad carbon and the way we use and where we use the carbon. Decarbonization gives a negative meaning to carbon that not always applies. In some cases, we really need. So, I mean, the question, carbon capture and sequestration, maybe we should revise our thinking, carbon capture from biomass, I mean, and reusing, relocating this carbon where we really need. What do you think?
I happen to agree with you. I've been following the so-called biochar discussion in North America for a long time. There's still a lot of unknowns in biochar, but we certainly have to reverse it. I'm well aware that in northern Italy, the soils are losing carbon, but there is a brilliant exposition of this. If you ever get a chance to go to Chicago, to the Department of Energy synchrotron there, the site has a piece of pure prairie that was never disturbed. It is 4 feet taller than the surrounding land because all of the farming of the pioneers in 2 centuries has burnt out the carbon and soil erosion to reduce the level. And you're right, we need very, very multifacets. There's no single solution. I'm reading a paper at the moment where a group, again in France, has looked at biofuels, land, and other objectives and said, if you go after any single one of them, quotes decarbonization say, then you're probably going to damage the other ones. So you need a much more integrated viewpoint and an acceptance that a solution for central US and a solution for Finland in the north is likely to be very different. And I think, again, I come back to my issue at the end of my summing up. If we don't innovate, we're definitely not going to work it out. And we have to be very, very innovative to make this work. And I really thank you for your question, David. It's very reflective.
Thank you, Ralph.
Thank you, David. Next question will be from my colleague, Nicolas Bazoglou, professor here in Sherbrooke. Nicolas, if possible, open your microphone and your camera.
So hello, Ralph. It's always a very big pleasure and very emotional to exchange with you. And you were among my most important mentors. And as I grow older, I realize more and more how this mentorship was important in my professional life and also personally. Nicolas, so
you're making me feel very humble. I was just having fun.
Yeah, me too. In fact, and having fun, it's one of the most important parameters in the exchange between people, and this is, I think, what we feel, both of us. In fact, I have a question which is related to the hydrogen economy and also renewables. We know that we have a big problem with plastics in our society. Using plastics to make energy and hydrogen fall well within the hydrogen economy. And also, we can compare it with biomass. But my question is how the world or our community considers the waste and waste plastic inside what we call renewables. I know most of the plastic comes from oil. Oil is a fossil, so it's not really a renewable. But with all this crisis of managing these waste streams, which are essentially a big trouble for our society, makes that biomass and waste are combined in doing the hydrogen and also using it as an energy vector. So where we are in this thinking process about waste streams, plastic waste streams?
There are actually 2 or 3 levels of answer to this. The first one is sometimes the one given by the purists who have assailed me for 40 years in the biomass business of extolling the use of waste, because they really do feel that if you build an infrastructure reliant on waste to provide energy or materials, then when the waste start to disappear, you've got a stranded asset. That's practical. It also, this is slightly moral take. My response is a little more off kilter. You remember the diagram of where the carbon came into the atmosphere and where it turns up? We went from 286 parts per million to 417. So that increment, which is very large, is mostly fossil carbon. And when you grow a hectare of corn, that fossil carbon comes back in the biomass. Mm-hmm. So I take the viewpoint that so-called using plastics as non-renewable is crazy. It's part of the flow of carbon, and if you get a second and a third use out of it, then why not? You're reducing the impact, and eventually you're reducing the need to draw down further fossil carbon, and hopefully the innovative process will be providing those materials from renewable carbon. So I'm very agnostic about where the carbon came from in the recycling. Once it's out of the ground, you should use it to the best effect.
Thank you. Very clear answer, and very positive. I think we are invited to work a little bit in this direction and put more endeavors. Thank you very much, Ralph.
Pleasure to meet you, at least over this medium.
Yeah, we hope we have been able to meet after the pandemic. So we are just expecting to have this vaccination, and hopefully we can meet in the near future.
I think it's going to be 2022, not 2021.
Maybe.
Yeah, I suppose so. Yeah.
Thank you, Nicola. So if we don't have any other questions from people attending this seminar, I think for the interest of time, we will close it. Again, we are honored having you with us today, Dr. Overend. Really a pleasure to hear your talk. Hopefully, again, I will meet with you in the close by future, if possible, maybe 2022, as you mentioned. So that being said, again, thank you. We're going to wrap this up, but just before we wrap this up, next week, we're going to have a talk on Power to X. So we have been talking about Power to X. My colleague Bruna, that intervened previously, will be talking about Power to X. And the week after that, we will have people from Carbon Recycling International in Iceland talking about what they're doing there in terms of Power to X. So again, Dr. Overend, thank you very much. Thank you for all you guys attending this seminar, and have a great week. Thank you again.
And I thank you very much for the invitation and the stimulation you gave me to put together my rather random thoughts into something I hope was more coherent. It was a pleasure.
Thank you.
This is Jean-Michel. Hello, Ralph.
Thank you.
Thank you very much.
Thank you, Mary.
Thank you. Bye.
So, Dr. Overend, are you still online? He's
No.
left. Okay, fine. Thank you, guys.
Thank you, guys. Bye bye.